Okay, so let's get started. Thank you for joining. This is Exploratory Online Seminar number 33. This time, I'd like to present Exploratory Data Analysis Part 3, association with categorical variables, basically. Before getting started, let me introduce myself. My name is Kan Nishida, a CEO at Exploratory. Exploratory, we started it 2016 spring, so it's almost like 4 years. So since this 2016, we've been basically building Exploratory as a product that makes it easier for you to access data science. And also, we've been providing this type of seminar or training to share our knowledge and skill so that more people will have better data literacy and then the skill of the data science. So prior to start Exploratory, I used to be working at Oracle, which is known for a database and software company. And I was development director, developing various types of data science products, and so on. Okay, and then so our mission as Exploratory is democratizing data science. We think, it's already happening, but more people use data to make better decisions. So the data science turned out to be a great tool. So we want to make sure that everybody has access to it, and to the point we are now going to have the word called data science. So when you say data science, this is the workflow we mean. So usually you start with your business questions or problem, and you want to answer or you want to solve the problem, and then you want to use the data. So you access the data, collect the data, and then usually the data you just get is not ready for even visualizing or analyzing. So you want to use data wrangling. Basically, you want to clean the data and then transform the data to the in a form you can visualize to understand, or you will analyze to understand. And then you want to use a visualization, basically the charts, so that your eyes can detect the patterns and the trend in the data. But the problem is your eyes have a limited, we are human beings, so we can see only what we can see. So that's where we have analytics tools like machine learning or statistics, so that we can use the machine to find the patterns and the trends in the data that our eyes couldn't see or might have been deceived. So we go through this data access, wrangling, visualization, analytics, going back and forth in any order until you find some insights that can help you answer the questions or help solving your business problem. Once you find such insights, then you want to communicate to others so that not just you, but as a team or as a group, you can make better decisions. So we built Exploratory to make data access, data wrangling, visualization, analytics, and communication easier by providing the modern and simple UI. So that's really Exploratory about. So enough for the introduction. So let's get started. Exploratory Online Seminar number 33. So exploratory data analysis is the topic that we've been talking about. I have done that part 1 and part 2, and this is the third episode of this series. So exploratory data analysis part 3, association with categorical. I want to actually kind of start off is something that I've been talking about, just to kind of refresh your memory if you haven't watched it before or you kind of forgot. So there's an ice hockey player called Wayne Gretzky, and one of his famous quote is, "I skate to where the puck is going to be, not where it has been." And it's super cool comments. But what it's really saying is basically you want to predict, right? So you want to predict where the thing's going to be or how the thing's going to become. And for example, the customers, how much customers you're going to have, you want to predict that. Once you predict, then you can be ready. You can do something so that you can satisfy more customers. If you know there will be no customers, and there's no point of spending any resource. So you want to predict, right, any business. But I would go further to say, I control where the puck is going to be, not the puck controls where I should be. And then I put the word control, and obviously this sounds cool, but it's very hard to control. And then probably that's why like I never become a good ice hockey player. But this is about the control. So not just predicting, but you want to make the future the way you want. So what can we do to make that happen? Like let's say like you want to have like 1,000 customers by end of this year. What can you do to make that happen? So that's control. So either you predict or you control, you want to start with hypothesis. For example, maybe the weather might affect to like a number of the customers. So like you want to see like, okay, it's going to be like warm weather. Then if it's warm, like you're going to expect like this number of the customers or something like that. Or maybe like you discount affects the number of the customers. So if you know it, then like you can actually, let's say like you offer a 10% discount, they might increase the 10% number of the customers or something like that. Either way, you want to start with hypothesis. When you have the hypothesis though, you have to make sure that you test it because you have hypothesis can be wrong. So typically in the science, and you use the data, you experiment, you collect the data, and then you do the you evaluate, right? So that right-hand side it says test, and it typically means it's hypothesis test or A/B test in a modern world. And make sure whatever the hypothesis you came up with is actually valid with the real world or the thing you're seeing. But that is called confirmatory analysis. Then the question is, how can you come up with these hypotheses? Well, typically you come up with hypotheses based on your intuition. You have many experience in your field or business. You have some idea. Idea is we are human beings. We are full of idea. But also someone said, hey, how about the data? You have the data, right? Instead of starting with hypothesis, you have the data. Can we build hypothesis from the data? So this is like 1660s and 70s around that time. This gentleman called John Tukey built a method and published a book called Exploratory Data Analysis. There's literally this book, and it's a really good book. I highly recommend. It's a little hard to read his writing, but it's a great, almost like a Bible in this field. But the whole theme is let's build a hypothesis. Let's understand the data. Then from the data, you can actually start building or exploring the hypothesis. So exploratory data analysis is really about an exploratory and iterative process of asking many questions and find answers from data in order to build the better hypothesis for explanation, prediction, and control. And then this part is asking many questions. You want to explore, like what are you exploring? You're basically asking many questions to the data and then trying to find answers to the questions you keep coming up. So then what questions you want to ask? Well, there are a lot of questions you can ask, of course, but there's a two principles. These are two sort of like kind of backbone when you do the EDA or exploratory data analysis. Number one is how the variation in the variables. You have the value. When I say variables, they're typically in the columns in the table data or Excel data. So there are a lot of variables, and then like how those variables vary. So like variation. The second one is how the variables associated to one another. And this is actually really important. And then sometimes correlation, but association, and those two things. And then I've done the seminar in the past. So like number one, the part one was about the variation. So understanding variance. Number two, part two was about correlation and association. So if you haven't watched, I highly recommend go to our website, exploratory.io, and then under the Learn tab, and there is an online seminar. On that page, you scroll down to the bottom, and then you see the link to the past seminars, and you find two seminars listed there. Okay, so the association and the correlation, just to refresh, a relationship where changes in one variable happen together with changes in another variable with a certain rule. So that's really the association and correlation. What's the difference between this association and correlation? Association is any type of relationship between two variables, but correlation is a little bit more strict. A certain type of usually linear association between two variables. And usually this typically means two numerical variables. And some people really care about the difference between the correlation and association in terms of the wording, and I think that's important. I respect that. But at the end of the day, what we want to find is a relationship among the variables or between the two variables. So to me personally, it's not that important. It's just that like a relationship. Nonetheless, so association is this case like country and a numerical. Monthly income is a numerical and a country is a categorical. So category and numerical. So okay, maybe instead of calling correlation, let's call it association. But here is when the country change from US to UK or Japan, the monthly income change. And then, there's a variation to it, right? So it's not like one single value, but you can see, once you know the country, you can see, hey, this is the range for the monthly income or something like that. And the correlation is age and monthly income. Notice that age, the x-axis, that is numerical. So based on your age, you're 25 years old, you might make this much as money or something like that. Okay, so that's the correlation. So this is important because finding a correlation or association, you can start predicting based on, for example, in this case, even though you don't know like this person's monthly income, but once you know this person's working years or age, you can start predicting or estimating their income. So if you find a strong correlation, then it makes it easier to explain how your subject of your interest, such as income or sales, number of the customers, changes and predict what monthly income will be, or sales will be, or number of customers will be. And then one thing I have to say this is kind of like a cliche, but correlation is not equal to causation. So causation is a special type of correlation. So just because you find a correlation, that doesn't mean that one is causing the other. It happen to be like two of them can be the causation sometimes, but sometimes just happen to be just heading to the same direction, and it's usually caused by something else that you don't see. But if the correlation or the association is turn out to be the causation, that's amazing because now you can actually control the outcome. So so there's that. So now, okay, so that's the sort of like kind of freshing up the basic of the EDA. So now, how about the relationships between categorical and logical variables? What I mean by that. So I'm going to use employee data again in this episode. And then there are variables, it says character data type. Then we call these categorical data type. Okay, so for example, the business travel or attrition, department, and so on. So in this previous slide, I think the right-hand side bottom that's a numerical. So that red square is wrong. I'm going to have to fix it. Anyway, so categorical is, let's say like American states, California, Texas, and so on. This categorical, basically no continuous relationship, and also no ordinal relationship. There's no, California should be before Texas and then New York after that. There's not that kind of relationship unless you bring numerical information such as population and GDP and so on. So, and then that's a categorical. And then here, attrition, this is categorical, but look at these values. There's only yes and no, right? And then this one, basically, did this employee quit? Like that's attrition, yes or no, right? So this is a kind of special type of categorical, and we call it logical data type. It can be considered as a categorical, but the categorical umbrella, there is a kind of a special type called logical. And it can have only two values, yes or no, or maybe like 1 and 0. And typically, we convert this type of data to true or false in the computer or in the system, or including exploratory. Okay, so this actually, what I mean by that is like, let's do it here. Oops. So I have the employee data here. Let me just make the screen bigger. Okay, and then we are looking at here. All right. And here's attrition. This is a character data type. And it typically, like if you know this is like a logical nature of the data, it's better to convert to logical data types. Then you can do a lot things easier. So let me just change this one to change data type and then go to convert to logical. And then I'm going to just click on run button. There's a function called str_logical. But nonetheless, the default, so yes becomes true, no becomes false. You can actually change it if you want in that function, if you like. But here, now like we know 237 out of 1,470 people have left the company, and then the other haven't. And those are like 16% of the people who left the company in this data. Okay, so now we want to understand this information. So what type of people leave, what type of people that don't leave. We want to understand the tendency or difference between those two groups. And that's really today's topic. Okay, let's get back to slide. Okay, so now, how about the relationship between categorical and logical variables? This episode, this seminar, like I'm gonna focus on specifically the logical variables. But I don't want you to get confused, because logical is part of categorical. So whatever we're gonna do, it can be extended to more than two values, like a categorical values as well. Most of the stuff. Okay, so let's imagine like we have an attrition and then a country variable, right? So both of them are categorical and categorical. And attrition in this case are logical specifically. So the relationship, if we have the chart like this, this is sometimes called bubble, sometimes called scatter plot, whatever that is. So x-axis is country, y-axis is attrition. Okay, and then the size indicates the number of the people there. So it looks like, for example, US and true has a lot more people than any other combination. You can use bar chart. Basically, this is the exact same thing, just presented in a different way. US, UK, Japan. Now, blue is actually showing the ratio of true. So again, US has a lot more, and then Japan also has a lot more. And when you look at this, and then basically you can say, well, UK, the people who live in the company, has a lot less than Japan and US. Even before we kind of see that, but also what's amazing is that this one, I just changed it to ratio. So before, like our eyes just kind of got focused on like US, because US has a lot more employees. But even here, if you present in the ratio, you can see that Japan also has a lot of people leaving. So in this case, like basically categorical, logical, those are like, true, false, or like Japan, UK, US. That type of thing is not numerical variables. You want to change it to ratio. Then you can understand the relationship. In this case, country and attrition. Okay, the ratio is a key here. So now then let's investigate how the attrition is related to other variables. Basically, like what we want to know is like, what is associated with attrition. If I expand the vocabulary in an unscientific, unacademic way, basically we want to see like what is correlated to attrition. Okay, maybe I shouldn't say, but basically what we want to know is the relationship. But what kind of relationship and what's related to attrition, right? What makes attrition true or false? Okay, so from here, let's use Exploratory here. What we want to do is like here, there's a correlate button. So you can click on this one. And then I have already selected. If you didn't select, and then you get something like this. So now from here, I want to do, let's say like attrition. This is a column that we just converted to logical, right? And then in order to be able to select this one, either numerical or logical. In the last episode, we did focus on the numerical. This time, we're going to focus on this logical data type column or variable. So now what we are seeing is a relationship between attrition and age, attrition and business travel, and so on. Let's take a look at here, business travel. The most left-hand side, it says travel frequency, and the ratio is 24%. So the 24% of the people who travel frequently have left the company. So that's pretty high compared to other two categories. For example, the people who travel rarely leave the company, 40% of the chance, or like 40% of the people left the company. And the lowest is here, non-travel. These are the people who don't travel at all. Then the 8% of those people who left the company. So they tend not to leave, but if you travel a lot on the business travel, tend to leave the company, right? So you can see like the sort of like this is a relationship, it's a strong relationship in a way between attrition and business travel. If you know the business travel status of employee, you can see this person tend to higher possibility of leaving the company or less possibility of leaving the company. Okay, so now here, let's take a look at this one, gender. And the gender, I'm going to here, male, 17% of male employee leave compared to woman, female, 14 or 15% of the female leave the company or left the company. So it seems like male tend to leave, more chance of leaving than the female. Okay, so there are this business travel, gender, both of them seems to have some type of relationship with attrition, but there's a difference between these two. So first, let's take a look at this one. It's basically, this is called error bar. So there's a dot at the kind of middle, and then there's a line. This line is 95% confidence interval. You can actually change it, but we're going to keep using the default, which is 95% confidence interval. Okay. So now here, what is the confidence interval? And then I covered this in the last seminar, but just to refresh ourselves real quick, because this is such an important topic. So let's imagine we have this like a 1,400 employee data, but this data might not necessarily all the employee in this company, or might not necessarily the correct data, because new employee keep coming, or some employee leaving sort of like every day, especially when you have a big organization. So that data you have might not represent the true picture. And what is true picture? Well, we want to understand the nature of these employee, or this sort of like a group, right? Then maybe like it happen to be like not included in this data, but there might be somebody outside of this data as well. So when you say, like, for example, 14% of the people left the company, but 14% might not really representing the true true number. So for example, let's say like this ratio, ratio of, let's say, like leaving the company is a 33% of this data, but that doesn't mean the true ratio, which is like in a statistics world, this is like a left-hand side is a population, right-hand side is a sample, but it's like a real thing, or like more accurate thing can be 31%. Then, but we don't know. I just made up 31%, but we don't really know. All we know is the percentage of this particular data, right? So now, if we don't know the true ratio of the attrition, what can we do? Can we do something like this, which is confidence interval, whatever? If we draw the line, then, or like range or something, and then we want to draw this line so that we can say 95% of chance that true ratio should be included in this range. Can we do that somehow by using some statistical method? Yes, you can. That's 95% confidence interval. So in the statistics world, like you can have this sort of concept of the population data is like basically all data, and you sample. subset of it, and then you repeat that process many times. And each time you calculate, in this case, ratio, and you calculate the confidence interval by using the same formula. Then you get ratio and the confidence interval. Every single time, the sample data is slightly different, so you get slightly different ratio and the confidence interval range. But the confidence interval range means within this range, if you do, let's say, like 100 times you samples, 95 of them, 95 of confidence intervals should include the true ratio. That's really 95% of 95% confidence interval. It can be 90%, it can be 99%. Typically, in general, we use 95% often. Okay, but and then this particular case, we happen to be seeing one of them, like 1 of 100 or whatever. So that's really the confidence interval concept. So that's sort of like kind of theory behind it. But the important thing is here, if we see that, let's say, the difference between these two groups, and then, but this particular, like 24%, it can be 25%, it can be 26%. In this particular data we have, it happened to be 24.91%. But it can be within this range by using 95, as a chance of 95%. So here, like 19 to 30%, right? So if you have the person who's travel often or frequently, they can, maybe like a chance of like they're leaving is like a 20%, 30%. But is that really different from other two categories? And then travel rarely is from the confidence interval is 12% to 17%, right? And then here's the important thing: these two confidence intervals is not even like covering each other or like any like touching or anything like that. So that means these two, the difference between these two can be considered as significant. Meaning, statistically, we can say these two are most likely different. And there, this is a 95% confidence interval. So like there's a 5% of the chance we could be wrong, but most likely these two are, there is a significant difference. So if that's the case, how about the gender? So this one is a male and a female. It looks like the ratio itself is different. Like male has a higher ratio than the female. But the problem here is including confidence interval, the range is covering each other. So that means maybe the female happen to be in this data is almost about 15%, 14.8%, but it can be like 16% or 70% around here. And male, in that case, if like in this data, 17%, but we don't know. It can be 15%, 16%. So maybe there might not be any difference, or maybe female happen to be even higher. So this is kind of tricky, kind of confusing if you're not used to it. Because hey, like I have 1,470 employee, all the data. There's no other data. Like, what are you talking about? What is the population? Well, if that's the case, this is the only employee you have to deal with for any future, or any time. Then that's it. You don't even need a confidence interval actually. But typically, new employee will come, right? So the next month or next year, or some employee leave. Then nature start kind of changing, right? And what you want to do is basically with this information, you want to estimate, or you want to sort of like predict what is going to happen tomorrow, next month, or next year, or new employee come, like what's going to happen to that person, right? So in that case, you want to sort of like extend what you're seeing here, and that's this confidence interval comes in. Okay, hope I'm making this clear. This is kind of confusing topic. But anyway, so now we can't say the female and the male, there's a difference, significant difference between the two, meaning we can't conclude there's a difference between these two. That means we can't say like there's a relationship between attrition and gender, meaning if the male is higher or lower, that the attrition, we can't really say that stuff. So then, this case is kind of easy. Sometimes the tricky one is the lines are a little bit like kind of covering. It's almost not covering, but it's a little bit, and that's the kind of tricky part. Maybe a good example here, for example, like this like 2 and 3. It's a kind of like a overlapping a little bit, but slightly. And in those cases, what you can do is you can do something called hypothesis test. So let's get into it here. So the gender and attrition, if you just focus on just the ratio, we forget about the confidence interval, then there seems to be difference. But the question is that difference or the relationship between those two really was paying our attention. Should we investigate more, or we should just move on? And if it's a numerical variable, that's what we saw last week, in the last episode. We got the confidence interval, but also you can do the hypothesis test, such as t-test and classical worries and some others, other type of stuff too. If you want to know the detail, please check that last video. But what are we gonna do if it's categorical? I mean, in this case, we are looking at logical. It turned out basically the same thing, a similar thing. If it's categorical, we have seen the ratio along with the confidence interval. But if you want to do the hypothesis test, you want to do more like sort of like a more what do you say? Maybe like rigorous or like more like correct way, then you can do hypothesis test. So there are two ways to basically conclude, okay, there is a significant difference. So there is a difference that we should pay more attention to. Okay, so that means you don't even have to do the chi-square test. If you had the confidence interval and there is significant difference there, there's no point of like going to the chi-square test. Okay, and then you can ignore the confidence interval. Like, you know what, like I'm not sure about the whole confidence interval thing. I'm more comfortable with the chi-square test or hypothesis test. You go to the hypothesis test and you don't bother the confidence interval. But it's better, I strongly recommend you want to use confidence interval first. And then if there's something that you want to even go further, investigate further, then you want to use the chi-square test or the hypothesis test. Because hypothesis test is a little tricky. There's a null hypothesis and a p-value and different concepts. So, but anyway, so I don't want to go into too detail on that in this episode. So anyway, so chi-square test is about to test if a given pair of two categorical variables are independent or not. When I say independent, there's no relationship between the two, okay? So another way to put it, we can evaluate if the relationship between two categorical variables is significant or something that is worth our attention. Okay, because the word significant is a kind of confusing word. So it's basically like, hey, this seems to be like some kind of difference that we should spend more time, or we should move on. That's really what the significant really is. So here I got like a male and a female and attrition, and I just draw a bar chart, stack bar chart, and blue is true, right? But again, when we compare the categorical and categorical, in this case, in attrition and gender, and then you want to change it to ratio, then we can really compare between the two. And then looks like female has more true and than the male. In this case, this is fictional stuff. It's not based on the employee data. Then we can say, hey, seems like that ratio-wise, there seems to be some difference, but is this difference significant? And then if no relationship, let's say like gender and attrition, you know what, it doesn't matter. It looks like, there's a difference, but it actually doesn't matter really. Then in that case, this is sort of like theoretical, when there's no relationship between gender and attrition. So same ratio, right? Let's say like both of them like around like 80% or something like that. Then we can say, okay, so there is no difference between these two. But so that's the, sometimes we call it null hypothesis. There's no relationship. But now, if we assume that there's no difference between female and male in terms of attrition, or there's no difference between attrition and gender, right? And whatever the difference we are seeing in this data, how far from that, there's no different status, right? Or maybe whatever the difference we are seeing can be explained by just variance that we cover in the first episode. The just variance. I mean, in this world is random, so like you never get every single same value every single time. There's always difference, but so maybe this is part of it. So it's like a marginal difference. So what I mean is the left-hand side is actual data. This is the data that you visualize the data you have. Right-hand side is a kind of theoretical when there is no difference between the male and female. And then the question is how different, how far from the theoretical. So that's what the chi-square test is. I'm not going to go into the detail of the calculation logic and all that stuff, but in a nutshell, chi-square test is to calculate the chi-square value, which is based on the difference between this actual data and the theoretical values. Okay, difference of like a kind of this ratio. I mean, like right hand side is basically no ratio. I mean, no difference, and then how far from it. So that's really the chi-square value is. So now here you can see the p-value, which is 0.2588 at like about 26%. So what p-value is, again, like we covered this p-value in the last seminar, so I'm not going to go into the detail, but it's really, p-value is about if we assume that something called null hypothesis, basically the no difference between, no relationship between attrition and gender, or no difference between male and female in terms of attrition, either way. Then what is the chance that we would see this kind of difference? In this case, male ratio is higher than the female ratio. What is the chance of seeing or getting this? Maybe like if it's marginal difference, then maybe it's like 50%, like just a coin flip or something like that. But here we see 26%. So about like 1 in 4 times, and you would see something like this. Therefore, it's not that rare. So like we can still stick with the assumption. What was the assumption? Well, that we assume there's no difference between attrition and gender. So we're gonna stick with it. We don't have to change it because 1 in 4 chance like we get this kind of thing. So we can't really conclude there's a relationship between gender and attrition. So now let's take a look at job role. In this case, the p-value is, it says less than 0.001. So that means 0.01%. So less than 0.01%. What that means, if we assume if we assume there's no relationship between attrition and job role, the chance of observing the difference we see here would be close to zero, right? Almost like 0.01%. So, it's not going to happen. But it's happening here. So therefore, hey, this assumption is kind of not working. It's contradicting with what we see. So therefore, we can just kind of throw away that whatever the assumption we had or null hypothesis. That means we can conclude there seems to be some relationship here between this job role and attrition. So that's what we are seeing here. So I'm gonna just So what that means is here, so like we are looking at the job role here, p-value less than 0.001. So from here though, now what we can do is we can even go further by using this chi-square test. So from column header menu, there's some menu here, but at the bottom, there's a create chi-square test. And if you click on this, you can basically create the chi-square test under the analytics view. And the p-value we are looking at is here. It's the same thing we are looking at. And hey, how come this is not 0.00001? Well, because this one looks like a 2.75 and it looks like a big number, but it's actually, it says E minus 15. This is called scientific notation. This means 0. If you say 15 times, so like 0.0000015 times, then 2752. So that's what that means. So that means it's very, close to zero, very tiny number. So again, if it's a p-value is close to zero, that means we can reject the null hypothesis. In this case, there's no relationship between attrition and job role. Therefore, there seems to be some relationship. And why that is that case, we use this chi-square. That indicates how different from the null hypothesis or no relationship status. So then when you go to the contribution percent, this chart will tell you which combination is the one makes that difference, makes that difference to be significant. And then the size is meaning number of the data size, or in this case, number of the employee. So bigger the circle, the more people are there. But the color is the contribution ratio of towards to the chi-square values. So for here, it's a contribution 33.37% at the bottom. This, it means 33% of the chi-square value is coming from this particular combination, which means the reason we got a higher or bigger chi-square value is because this combination contributed a lot. So what that mean? Well, sales representative and true. You can go to the ratio here, sales representative true. So it looks like there are a lot more people in terms of ratio leaving in the sales representative compared to other job roles, right? So this is the one that's significant, something like something going on compared to other category or combinations. So that's what it is. So if you get confused with the chi-square value, probably so. If you not, this is the first time you heard it, then I recommend you to use this ratio. But then the ratio, maybe like this, even for example here, well, it looks like there are a lot of people leaving, but maybe there are only like, let's say 10 people here compared to 50 people, for example. Then why you pay attention to 10 people, right? So that's what this contribution tab actually help you, where you should focus. And that's where, enough amount of people, enough amount of the evidence there. And then like you want to actually go to the ratio, then you can understand more intuitively. Okay, so that's now like we have seen the difference or relationship between attrition and other variables. We start kind of getting this idea, and the job role seems to be like based on the job role, the attrition rate is different. So from here, another thing, like we want to investigate even further by using the logistic regression model. We don't have enough time, so like I'm not gonna have enough time to kind of go into what the logistic regression really is. I'm planning to do that as a separate session, seminar. So, but today though, I wanna actually jump into building the logistic regression model. But having said that, it doesn't have to be logistic regression. It can be decision tree, it can be a random forest, XGBoost. These are machine learning model. I'm going to use logistic regression because this is a statistical learning model as opposed to the machine learning model. So I'm going to use that. And also another reason I want to use it is because here it says AUC, and AUC is the indicator or the metric that shows you how this particular variable, in this case, job role, can separate attrition true employee and attrition false employee. That means AUC is sort of like kind of a proxy of the correlation between job role and attrition. We want to know like how strong is the relationship between these two variables, and AUC actually gives you that sort of a kind of proxy metric. Especially this is used for when you have like a logical variable. Okay, so and that AUC, how we calculate, well, we build the logistic regression model for every single combination, so attrition and age, attrition and business travel, and we build logistic regression, and then we calculate the AUC based on the model. So that's why like I want to actually use logistic regression this time. By the way, though, here's the sort, so I can change that to AUC. And that means now it's all the variable is being sorted based on the AUC values here. And higher the AUC typically from like a 0.5 to 1. 1 is the highest. That means 1 is like, hey, perfect relationship between those two. If you know the job role, I'm 100%, I can just know who is going to leave, who's not going to leave. So here, 0.67, not super high, but among all those variables is the highest number. So we can say, like, for example, job role, total working years, those are the variables have a higher or stronger relationship with attrition. So let's take a look at, like, what type of relationship here. So I'm going to just go in here and set logistic regression. This is going to create the logistic regression model. Basically, what we see here is nothing different from what we saw in the summary view. Basically, you're seeing at the y-axis is the probability of sales representative people leaving or laboratory technician people leaving. So the gray, I'm going to just click on the blue. So what we see, this gray color, this has nothing to do with prediction or anything like that. This is actually actual value. In fact, this is exactly the same as what we saw in the summary view. But here's the predicted. What's predicted means, well, we built the logistic regression model behind the scene, and that model is predicting. But in this case, though, it's basically the exact same value as actual. So there's no point of even like building a prediction model here in this case. But nonetheless, in the categorical case, it's exactly and when you have only one single predictor variable, that's what you get. So now this is one single value, then you don't even have to do this. It's just, you kind of, there's not much new information you're finding. There's just a little bit more when you go to coefficient and all that, but pretty much, same information. But what is really cool, when you want to use a logistic regression model, is when you have multiple variables. So what I mean by that, so let me just go into here. Oops. So we know both here, job role, total working years have a relationship. Not just these two, but even like monthly income, overtime, job level, all of these variables seems to have a relationship with attrition. But let's focus on these two variables. Right, so we are looking at this kind of relationship right now. Working years, attrition, job role, attrition. I put the arrow to the attrition because we are focusing on like what makes attrition true, but we don't even know the direction in this case. But I'm just kind of like simplifying here. Okay, so now how about working years and the job role? There might be a relationship between them. The reason I'm asking this question is because job role, when the sales rep people seems to have higher ratio of leaving the company, but if there's a relationship between these two, then maybe that's not because sales rep, maybe because of the working years. You just imagine sales rep people are, like only like 5 years of the working years, and then like less working years, the people tend to leave earlier or something like that. So I use a summary view. This is just a screenshot here, but I use a summary view and correlation mode and select the working years as a target variable and then sort by the R square, which is the metric to indicate the strengths of the relationship between the two variables, right? So now looks like here's a job role. Looks like there's a relationship between total working years and job role. When you look at the R square, which is 0.43, it's not like super strong, but again, just look at that error bar. Seems like based on the job role and the working years is different. It's actually the most right-hand side is a sales rep. So it seems like the sales rep happen to have shorter working years compared to other job role. And then, so now we get kind of confused because working years and job role, there's a correlation or like association, right? So does that mean is working years is really having an effect on attrition, or maybe job role is the one having the effect on attrition? And when the job role change, working years also change. So therefore, as a result, it looks like we are seeing like working years and attrition are correlated or something. Either, the other case as well, when maybe like working years is the one really having an effect on attrition in terms of like attrition, true or not. Then working years shorter, then job role happen to be sales rep. Working years longer, job role happen to be like manager or something. So we don't know like which one is causing, or maybe both of them having an effect on attrition, but just like they split some like effect in terms of like how the attrition change. So how can we estimate the independent effect for each variable? What if just working years, we just forget about job role? What if only the working years change? What happens to attrition, right? So in that case, what we want to do is we want to hold one of the variables constant, not change. Like job role, for example, like a sales rep, only the salespeople. Then if we change only working years from 10 to 11 or 11 to 12 or something like that, does attrition change? The ratio of attrition change? If that's the case, then we can say working years have some effect on attrition. And the other case as well. So if we hold working years constant, let's say like only the years of 10 years or only the 15 years people, only 20 years people, then we see like, a difference between sales rep and executive or sales rep to, other category. And then the attrition really changed, the ratio of attrition change. If that's the case, we can say, okay, it looks like job role actually have something to do with attrition. So that's what we want to do. Okay, so here we have the attrition as a target variable, right? And then we were looking at the job role, and we know this total working years also have some relationship. We're just focusing on two. We know there are other variables also, but let's focus on just two to make simplify. And I'm going to just select these two variables. Then you can create a logistic regression based on these two as a predictor variables. Okay, and so I'm going to select this one. And what just happened is it built the logistic regression model with these two variables as a predictor variables. Okay, job role and total working years. And then target variable is still the attrition. And then basically like we're looking at here is sales rep, okay, still higher. But notice here, now the actual value was almost like a 40%. Then now the predicted value is kind of lower, which is now 34%. The why we have this difference, because these differences are coming from the change in total working years, which means if the total working years stay the same or exclude the effect of the total working years, only job role change, then like if you have the sales rep, then this 34% is a chance of people leaving the company. The other side as well, I think this curve, like if you happen to be creating logistic regression model only with working years, the curve should have been more aligned with the actual value. But now this is kind of a little moderate slope. And that's because now whatever you're seeing here, this blue line is excluding the effect of the job role, only the total working years. So now, like if your total working years are around like 5 years, then like the chance of leaving is about at the bottom probability is like 0.818, so like about like 20% or so on. Okay, So that's the kind of question you can answer with the logistic regression model. And then now we have two, right? Job role and total working years. Which one has more effect on the attrition? Which is more important if you want to predict if a given person is going to leave or not? That's where you can go to the importance. And then you see like job role is, this is like a relative importance. So this value doesn't really mean anything, but just relatively comparing job role has a lot more effect on the attrition compared to total working years. So in this company, like you want to find out what the job role is first if you want to know this person it might be leaving or not, that kind of stuff. Okay, so that's actually all. So what we found is, okay, working years, job role, both of them have effect on attrition, but it seems to be like job role has much more effect on attrition. That's so these are the kind of things you can do with EDA or exploratory data analysis. In this episode, we focus on the categorical, specifically the logical variable. Okay. So that's it for today. And next week, I'm planning to do is how to start exploratory for Excel users. We have a lot of Excel users, ended up using exploratory, and it's we hear a lot of sort of kind of a stumble blocks when they start using exploratory. So I'd like to cover, these are the things. If you know it, then your life would be much easier. That kind of stuff. So that many topics. So I'm going to just do the part one and part two. So these are 2-episode series. And at the same time, next week, 11 a.m. Pacific time, 2 p.m. Eastern time next Wednesday. And hope see you there. And you can find our online seminar from the header area LAM. Go to the online seminar, and then you can find the future schedule or past seminars. Okay, that's it today. And make sure you follow Twitter at Exploratory Data. And we keep sharing a lot of information, many information that we think is useful for you. Okay,